Last class in section 4.2, we discussed a lot of different things about logarithms, including the properties of their graph, the characteristics, the shape. We also started to talk about evaluating them in the calculator using the log and the natural log button. Today, we're going to expand our abilities to utilize these logarithms by expanding and condensing them using the product, quotient, and power rule. But these are the same exact rules with logarithms as they are with exponents. So our first rule today is called the product rule. The product rule is the same as it is for exponents. In exponent world, the product rule means that if you are multiplying the bases, you add the exponents. So if we are multiplying inside our logarithm, we can separate this or expand this by adding two separate logarithms together. So multiplying becomes adding. That's the the product rule. So if we see this in real time, it says use the product rule to expand each logarithmic function. So I have log base 4 of 7 times 5. So I can separate that into two separate logarithms. Log base 4 of 7 plus log base 4 of 5. So we can expand, that's the word you're going to be seeing, we can expand these. If there's multiplication inside, it becomes addition with two separate logarithms. Yes? Easy peasy.
Wait, can you repeat that?
If we are multiplying inside a logarithm, it becomes addition with two separate logarithms. Multiplying, add, yes, same base stays the same, just like it did with exponents. If we do question B here, what is the base of this logarithm?
Well,
10. It's our common logarithm with the base 10, so we don't write it. Which means if I separate this, if I expand it, this is going to be log of 10 plus log of x. Your spidey senses are probably not going off right now, but they should start to go off because since this is a common logarithm, it's base 10. Does anyone remember the rule when you had a base and an evaluating number being the same?
ooh, it was
Log base 10 of 10 is equal to 1. So I can keep going, and I can actually reduce this to 1 plus log of x. That's actually how we would want to expand this. So if we can use those properties that we discussed last class, which is log base b of b equal to 1. Yes?
What did you write with the M in the top right?
Oh, MA, which doesn't make sense until we write all three of them down, and then I'll make it make sense. MA, multiply becomes adding. Sound good? That's the product rule.
Did you just put the 10 on this side? Not on the, with the X.
You could. We don't need to, though. I only needed to see that base 10 so I could visually see that the 10 and the 10 cancel. Yeah, but it is there. We just don't need to write it because it's a common logarithm. The second rule for today is called the quotient rule. The quotient rule happens when we are dividing inside a logarithm. But what is this rule saying I do with these logarithms to separate them? I subtract them. So we're going to put ds right here for divide, meaning subtract. The logarithm of a quotient is the difference of those logarithms. So again, when we're expanding or condensing, these rules apply. So if we use the quotient rule to expand here, the base never changes, but I see that there's a division problem. So this becomes log base 7 of 19 minus log base 7 of x. Okay, let's apply that to B. Again, I see that there's a division problem, so I can separate this or expand this at the division problem. The natural log of e to the third power minus the natural log of 7. Again, our spidey senses might not be going off just yet, but hopefully you start to remember something else here. Natural log is base what? E. So I actually have a base e and an evaluated number of e. What does natural log of e to the third power become? Sort of. This part becomes 1, but then I have a power 3 up there, right? So it actually becomes 3. So if you flip back in your notes, I think just like 2 pages back.
Oh, and then we just crossed it out and kept the exponent.
Correct. We like did this number where we boop, crossed it out and kept the exponent. That's another property of logarithms. Inverse property of logarithms, if you will. Okay, so there is like simple expansion, and then there's expansion with extra when you can't help yourself but do a little more. That's the second rule for today. That's the quotient rule. The third rule is called the power rule. This is when you have a power raised to a power for exponents. So for us, it's a logarithm raised to a power. When you have a logarithm raised to a power, do you see this power up here? Where does that p go when it's equal to? Where does it move to? It like jumps over here, right? So if we have a power on our logarithm, we are going to multiply that logarithm by the power. So I'm going to say power becomes multiplication. A logarithm of a number with an exponent is the product of the exponent and the logarithm of that number. So it's like the exponent just gets to float to the front, and it becomes a scalar for that logarithm. Can we practice that for a second? So if I have log base 5 of 7 raised to the 4th power, these don't cancel because they're not the same number. So instead we're going to take that 4 and we're going to drop it in front of the logarithm. This becomes 4 times the logarithm base 5 of 7. Just bloop, drop it in front and multiply it. The only way this could get really any harder, this rule, is if it looks like this. This says natural log of square root of x. What's the power when you have square root of x? To the 1/2. So if I rewrote this, this is actually natural logarithm of x to the 1/2. And now that I see the exponent, I'm going to drag it to the front and plop it in front as a scalar. This is going to be 1/2 times the natural logarithm of x. So we want to see what those exponents are to be able to expand it correctly. And then last but not least, we have log of 4x raised to the 5th power. I see that we have this exponent here, so we're going to drop it in the front. So this becomes 5 times the logarithm of 4x. Just using the power rule, I would be done. But do you notice we have a multiplication problem here inside this logarithm? When we had multiplication, how could we separate this? Multiplication was, look at the very top, adding. So we can actually separate these and add these logarithms together. So we would have 5 times the logarithm of 4 plus the logarithm of x. You may or may not need to do that second expansion. This one technically only wanted us to expand using the power rule, but like I couldn't help myself. If we have a product, we can still expand by the product. Now these 3 rules are very easily remembered with this acronym that we have now written down on the sides of our paper. MADSPM. So at the top of these notes, I want you to write down the following. MADSPAM. Have y'all heard that before?
Yep.
Yeah, good. Multiply means add, divide means subtract, power means multiply. That's the rules for exponents, and it's the rules for logarithms, which is really nice. They're inverses of each other, so their rules are very much related. Multiply becomes adding, dividing is subtracting, power to a power, multiply. Questions, comments, concerns? Because now we're going to start mixing it up. I'm going to give you a condensed logarithm that has multiple rules to be used. And we're going to expand it following these 3 rules. MADSPAM. Are you ready? Too bad we're doing it anyways. Okay. So here we go. Expanding logarithmic expressions. Use the logarithmic properties to expand each expression as much as possible. The first thing I would like for you to do when you're doing these problems is to change everything to let the exponents be showing. Meaning, I'm actually going to take this logarithm, and instead of writing the square root of y, I'm going to change that to y to the 1/2 power. Because I want to see all of the exponents in exponent form so that I'm prepared to do something with them. Now, I have some multiplication happening inside this logarithm. How do I separate multiplication? Adding them. So the first step here is log base b of x squared plus log base b of y to the 1/2 power. We've separated it into multiple logarithms, and now we just take these powers and we deal with them. The power rule tells me I can do what with both of those floating numbers? Move them to the front. So this becomes 2 times the log base b of x plus 1/2 times log base b of y. And that is the expanded form of that single logarithm. So we're just using the rules to expand these different expressions into larger or smaller expressions. Okay, if we're working on b to expand this logarithm, there's a whole lot happening here. My recommendation is to always in your work show the exponents first. So we're going to change this to log base 6 of x to the what power? Cube root of x can be rewritten as what? 1/3, very good. So the 1/3 power. And then I have 36, and then I have y to the 4th power. Okay, now we see everything. Let's take care of one piece at a time. Let's take care of this division bar. Everything on top will be positive. Everything on bottom will be negative, meaning we can expand it to start looking like this. We have log base 6 of x to the 1/3 minus the quantity log base 6 of 36 plus log base 6 of y to the 4th power. Now, why did I put this little plus sign right here? Why do you think this plus is here? I separated them. In this denominator, aren't 36 and y multiplied together? So multiplying becomes adding. Okay, let's get rid of these parentheses because they're a little extra. So I'm going to distribute that negative to both pieces so that we have log base 6 of x to the 1/3 minus log base 6 of 36 plus log base 6 of, just kidding, not minus, not plus, sorry, minus log base 6 of y to the 4th. Now before we go on, my spidey senses are going off for log base 6 of 36. Aren't 6 and 36 a part of the same power family? Yeah, how can I rewrite 36 so that it's base 6? Isn't 36 6 squared? Oh, snap. And then I have log base 6 of 6 raised to the 2nd power. What does log base 6 of 6 do?
Cancel out.
It like cancels out, so then I'm left with a 2 right there. I'm also, just to save some space, going to start tackling these exponents here. Based on the power rule, where do I move those exponents? To the front. So they're going to drop in front here. And so our final answer would be 1/3 times log base 6 of x minus 2 minus 4 times log base 6 of y. That's the fully expanded version of that logarithm. Questions, comments, concerns? Huh?
What if people use log for in life?
Logarithms themselves actually do model a lot of like real life things. Let me see if I can think of one right now. It is the inverse of exponentials. So if you're ever working with exponentials, which is like pandemic growth, exponential decay, so like forensic science, if you're ever trying to work backwards in a problem, to work an exponential backwards, you would need logarithms. Also, a lot of things grow pretty quickly and then taper off at the end. So if you're ever measuring something and it grows really fast, but then it stops growing as fast, but it's still growing a little bit, that's a logarithmic function. So thinking like when you buy a car, when you drive it off the lot, it's worth a lot less. And very quickly your car depreciates in value, and then it starts to level off. Like you're never going to get $0 for your car. There's going to be worth something. That's pretty much a logarithmic function. It would be down like that. But these skills right here, the reason we're expanding and condensing them is because these are the skills we will eventually need next class to solve logarithmic equations. So this is like pre-work skills. Good questions. Just in case we can get this through before lunch, let's see if we can do just example 5. We can work these examples backwards, these kinds of problems backwards. This is already an expanded logarithm. We want to condense it and work backwards, meaning if I see that there's a plus sign, what can I do with the two things inside those logarithms? Adding went with what? Multiplying. So I can put these together into one logarithm and do 2 times 32 on the inside. I can condense them. So 2 times 32, that's log base 4 of 64. I don't really need these parentheses anymore. And then if I notice 64 is a part of the 4 power family, 64 is 4 raised to what power? 3. And if I notice log base 4 of 4, that's going to cancel out. We'd be left with 3. You won't always have to do that extra step of condensing it down to a single number. It just happened to be that 4 and 64 are part of the same power family, so we can actually do that. We'll stop here before lunch, and we'll pick this up after lunch, finishing example 5 and then the rest of this page. Continuing on for B here, what do you see in this problem that separates the two logarithms? A subtraction sign. Subtraction goes with which operation? Division. So when I put these together and I condense it, this is going to be log of 4x minus 3 divided by x. And like literally that's it. You don't have to do any other combining in any sort of way because you can't divide those numbers. Almost on time. All right, so let's do some more condensing, but we're going to do it in a little more complicated of a way. Let's write the following as a single logarithm. So we're working backwards. It's already expanded. We're working on condensing it. I see automatically that we have these numbers in front of the logarithms. Where can I put those numbers? As exponents. So we're going to toss them back there as exponents. This is going to be log of x to the 1/2 plus log of, and then I'm going to have to double parentheses here, x minus 1 to the 4th power is what's being argued, is the argument. Then I see that I have a plus sign right here. Adding becomes what? Multiplication. So we have actually the log of x to the 1/2 times x minus 1 to the 4th power. These are now being multiplied together. The only real thing we need to do here to clean this up, the way the book wants your answers written, I believe it wants all of your exponents to be whole numbers, which means we need to change that fraction exponent into a radical, a square root, yes. So we'd actually write this one as log of square root of x times x minus 1 to the 4th power. Both of those are equivalent, so just depending on what the instructions say, whether you can leave it as x to the 1/2 or you do need to create that into a radical. Just read the instructions to be sure. Can we try another one? No, too bad, we're doing it anyways. All right, what do you notice first? The 3, good. That's what I noticed first too, which means we can take that 3 and create an exponent out of it. This is the natural log of x plus 7 raised to the 3rd power minus natural log of x. What's the next thing that your brain is looking at here? The little minus sign. Minus becomes what when we're condensing? Division. So this will become the natural logarithm of x plus 7 to the 3rd power divided by x. And voila, we're good. So these rules can be worked backwards and forwards. Divide becomes subtract, so subtracting is dividing when you're expanding or condensing. Then we have this last one, kind of complicated. What should we tackle first? You got all these numbers in front of these logarithms. Let's take care of those first. So we move all of those to be exponents. This is log base b of x to the 4th power minus log base b of 6 to the 2nd power minus log base b of y to the 1/2 power. That's all using the power rule. They're all the same base, so I can start to condense them into a single logarithm. A rule here is that if you're subtracting, it means division, but if you're subtracting twice, that just means there's 2 things in the denominator, not a denominator in your denominator. So meaning I would have log base b of x to the 4th power divided by 6 squared y to the 1/2. Both of those 2 logarithms are negative, so they both go in the denominator of your argument. We just need to clean this up a little bit. We can expand 6 squared and we can rewrite y to the 1/2 as the square root. So the answer we'd probably want to stop out here is log base b of x to the 4th divided by 36 times the square root of y. Comments, concerns, questions? Okay. The last property we're going to work on today is kind of separate from the mad-span properties. It's called the change of base property of logarithms. The change of base property of logarithms allows me to type more than just common and natural logarithms into a calculator, because if you have, and I'm going to highlight this in a very particular way, if you're trying to evaluate log base b of m, you can actually do this by taking the log of any base of m and divide it by the log of that same base of b. Notice that the a is any number that you choose. Most likely, you're going to choose to use a common logarithm or a natural logarithm, since we have buttons for those on our calculator. So probably more helpful than this is writing this formula in this way. Common logarithm of m over the common logarithm of b, or the natural logarithm of m over the natural logarithm of b. As long as you use the same base on top and bottom, you'll evaluate the logarithm correctly. This is called the change of base formula. And let me prove to you that this works. So we need to evaluate log base 5 of 40. There's only a log and a natural log button on the interface of this calculator. So to be able to actually evaluate this log base 5 of 140, I'm actually going to type into my calculator common logarithm of 140 over common logarithm of 5, or I'm going to type in natural logarithm of 140 over natural logarithm of 5. And in fact, because it's our notes, we're going to do both. So if you have not grabbed your calculator, go grab it real quick so we can evaluate this common and natural logarithm and verify that they're correct. All right, I recommend using the fancy fraction while doing this just because it's easier to make sure you close the parentheses appropriately. So press the fancy fraction, log 140 over log of 5, press enter, and then also do it with the natural logarithm so you can see that this is the same thing. When you do log of 140 over log of 5, did you get 3.0704-ish? And do it again. If you do the natural logarithm, of 140 over natural log of 5, what do you also get? Yes, you should get the same number. Meaning it doesn't matter which base you pick. It could have been a base of 5. We just don't have a log base 5 button on our calculators. So it's a lot easier to do change of base formula using common or natural logs.